So I hope you're enjoying the course. So I think it is third week from last live session. Hopefully, uh, you might have uh, studying the tube wells and pumps, as well as some introductory lecture on drainage. So let me know if you have. So so let me review what we learned. I think last few classes. So in that, I think the last week we started the tube wells. So tube wells are very much essential in order to extract water from the groundwater. Right. So that is a source of irrigation. Uh, so in order to understand the design of a tube well, we should know some basic hydraulics. So I think we covered the basic hydraulics in week number, week number 5. Um, so we started the understanding of different soil water zones. So it's basically classified into unsaturated zone as and a saturated zone. And again, unsaturated zone is being divided into soil water zone, um, you would say weather zone and capillary zone. So, and then you have a saturated zone. And top of the saturation zone, we call it the water table. Okay, so our point of interest in case of groundwater is a saturated zone. And then, and also we started working on the different types of geological formations, such as aquifer, aquiclude, aquifuse, aquitard, right? So sand will make a good aquifer, whereas the clay and the silt could be avoided while considering and installing a tube well, right? And the types of aquifers like unconfined aquifer, confined aquifer, semi-confined aquifer, and burst aquifer. So these 4 we cover. And if you are installing well in different aquifers, like if you're installing well in unconfined aquifer, we call the well as a phreatic well, whereas if you are water table well, and if you install well in confined aquifer, we call it the artesian well. And also we call it as flowing well if the piezometric surface is above the top of the well. And if you are installing well in semi-confined aquifer, it's called semi-confined well. Whereas if you install it in a burst aquifer, called burst well. Okay, so the types of well depends on uh, uh, which aquifer your tube well is connecting to, right? And then the basic hydraulics, and also understanding the soil properties, right? Basically, in our case, so soil porosity is very important, void ratio, so and effective porosity, so and some other properties like specific yield, specific retention, right? Apparent specific yield. So there are several terminologies and also storage coefficient, right? Specific storage coefficient. So we covered, I think, the basic definitions of that, and also the properties of semi-confined aquifers, such as hydraulic resistance and that hydraulic resistance is C, and whereas leakage factor, that's B, covered. So then, based on the Darcy's equation, so we were trying to understand the steady state flow to well. So in case of unconfined aquifer, right? So as well as in case of confined aquifer, so derived some equations, for understanding or finding out the flow to a well in confined as well as unconfined aquifer. And then we started working on some water lifting devices. Um, so the water lifting devices, and then pumps. Pumps are classified as positive displacement and variable displacement pumps. So under positive displacement pumps, we learned the reciprocating pumps, rotary pumps, right? And then cam pumps, gear pumps, helical pump, diaphragm pump. So all come under the positive displacement pump. Whereas variable displacement pump, the centrifugal pumps, then axial flow pump, propeller pumps, jet pumps, and also special kind like hydraulic ram. So these pumps we covered, and also the basic definition of drainage, and so that's what I think we covered from the last live session. So I think we have some folks like Srinet. Good evening, sir. Yeah, Amana. Good evening. Hi, folks. Good evening. How are you doing? I hope you are enjoying the class. So let me know if you have questions. So I'll be looking at your questions in between, but let me keep talking because it should not get bored. Okay. Um, So basically, the water lifting as well as the pumps, water lifting device. Why this is lifting device? Why can't we call it as a pump in case of indigenous water lifting devices? Because here, if you observe the discharge is right at the like a central line of the pump. So only lift is we are considering. So that's why we call these indigenous water lifting devices. Whereas in pumps, so we have to pump from the above the central line of the pump. So that's the reason I think we call it the pumps. So you have a question like in lecture number 21. So problem 21.1. While finding Q, what does 1000 by 60 um, indicates? So let me, and also, sir, I am Aniket Singh, Agriculture Biotech. Sir, your lecture hopeful to make technical knowledge. Thank you. Let me find out, the lecture number 21 and answer his question. Okay. So we have the slides. Okay. So let me see where we have this files. It should be somewhere. All right, Abdullah, I'll be back at your question. So how to get internship under your guidance, student. So I think we announce, the internships time to time. So, but we don't have any official, certification or internship. But yes, so we do have internship opportunities if you are interested in. So generally, the NPTEL itself is promoting, to have an internship with me if you are securing, highest mark. So the top two guys are going to get internship under me. Okay, so that's a good opportunity. The NPTEL is providing to all participants, or right, all students. So that's one option. So secure good marks and be on top, like number one, number two, first number one, number two of this course will be given internship by NPTEL. So otherwise, we do have some internship opportunities. If you can write to me and let me know your, the area of interest. If you have some problem to solve, so definitely yes. Okay, it's a week 5, lecture 1. Let me see. Yeah, so I'm looking into the lectures. Okay, so here we do here. Okay, so Abdullah, so your question was, sir, in lecture 21, problem 21.1, while finding Q, what does 100/60 indicates, right? So this is a unit conversion. So when you convert, H to seconds and meter to liter, right? So the 100,000/60 will come. Okay, so I'm still locating the lecture number 21. Maybe, yes. So this is week 5. And All right. So still I'm waiting for the questions. Let me see. Okay, lecture number 21, and then slide 1. All right, so yeah, I got it. I got the slide. So this is when you are substituting the values for SL and SM and also L. L is in 2 mm per hour, right? So in order to convert the mm into liters and H is hours, so that's in seconds. So see, 1000 by 60 is been added. Okay, so hours into minutes, right? Hours into minutes, that is 60, and so that's 2 mm into liters. So that's why the 1000 uh, came into the thing. Okay, so because 2 mm to meters, 2 by 1000 will give you the meters. Okay, and then hours to minutes, so that's the 60, and then what happens, you will have the units in meter cube per hour, and in order to convert the meter cube into liters, so then you have to multiply with 1000. Okay, that's why there are 2000s here. Okay, so I hope you got it, right? Abdullah, are you still having the doubt? Because if I look at this slide, the slide that is 12th slide, when you are substituting it for SL and SM and L, right? So those units are in different units. If you see 7.8 meters, 6.5 meters, and then 2 mm per hour, right? So 2 mm per hour, that also you convert that in meters, so that 2 by 1000, right? So that is 2 meter per hour. Okay, but hours you just convert into minutes divided by 60, and since your units are in meter cube per minute, and when you're converting to liter per minute, again you have to multiply with this 1000. So that way the unit I mean, so that's why we have to multiply with 1000 by 60. Okay, and sir, how to get internship? Okay, this I answered the question. So any other questions, please let me know, otherwise we'll continue talking on the pumps that we studied. I think you have gone through that. Okay. So hopefully you understood what is the difference between positive displacement pumps and variable displacement pumps. So in case of positive displacement pumps, so what happens? The discharge won't change with head. Okay, so even if you change head, the discharge is going to be same. So that's a positive displacement pumps. Okay, whereas variable displacement pump, the discharge is going to change with head, right? So if you increase the head, the discharge is going to decrease. So it's inversely proportional. Okay, so and also we talked about single acting pumps as well as double acting pumps in case of positive displacement pumps. So in case of single acting pump, or for every two strokes you get one discharge out, whereas in double acting pumps, so for every stroke you get one discharge. Okay, so that's the difference. And we talked about the principle of lifting. There are several principles. So one is direct lift, let's say. There is one question. So, sir, please tell me about mud pump. Is it a type of reciprocating pump? Oh, yes, this is the kind of reciprocating pump. So, mud pumps we generally call, the uh, what do you call that? Mhm. So this is huh, come on, pneumatic pumps. What do you call that? So in diaphragm pumps. Okay, sorry. So the mud pump is also called the diaphragm pump. So since it doesn't contain any mechanical parts in it, so it has a diaphragm in one side, and if it is a single acting diaphragm. So the diaphragm creates suction, right? So that's going to pull the slurry out, and then yeah, this is a reciprocating, but of course you can study the diaphragm pump. Um, what else? And also there is even in variable displacement pumps. So depends on the type of impeller you use. So there is a particular impeller. It's basically used for the pumping the slurry. Okay, so that's a specific impeller used to pumping the slurry or mud water. So, and also, who is that, sir? Where can we ask our doubts at the time of studying itself? Um, so you can write to us if you have doubts, right? You just mention the lecture number and the slide number. So hopefully we will help you in that. Okay, you can write to me or write to the TAs. So definitely we'll sort out your doubts. And there is another question, Jayant V. Sir, explain various efficiencies in water requirement of crops. Wow. So the efficiencies you are talking, so we already explained those efficiencies in our lectures. But basically, if you are talking about efficiencies, so we start from canal source to, and then uh, yeah. So from canal to field level, okay, from canal to field level, we are going to talk about all those efficiencies, right? So the first efficiency you're talking, irrigation efficiency, we call, or conveyance efficiencies. Okay, so in case of conveyance efficiency, so we are going to see what is being delivered to the field and what is being conveyed to the field level, right? So that's the conveyance efficiency. And if you So basically, these are the water conveyance efficiencies. So the volume of irrigation water that reaches the farm, right? So divided by volume of irrigation water diverted to the water source. Okay, so that is the conveyance efficiency. And you have other type of efficiencies. Okay, so for example, you have water application efficiency. So that is, volume of irrigation water stored in the root zone divided by volume of irrigation water delivered to the farm. So one efficiency, that is application efficiency, the conveyance efficiency. So that is from source to the field level. Okay, so the volume of water you deliver to the field divided by the volume of water you have taken from the source. So the efficiency cannot be 100% because there will be losses when you're conveying from the source. For example, if you have canal or if you have other water courses, so while conveying from that point to the field level, there are some losses like seepage losses, evaporation losses. So exactly the amount taken from canal may not be same you are delivering to the field. So that is conveyance efficiency. So then once you got that water at the field level, so you are going to apply into the field. So that's called water application efficiency. And in this case, we are going to see the amount of water you applied, how much is really adding to the soil reservoir, or we call root zone depth. Okay. So that is VF is we call volume of irrigation water delivered to the farm field, that is in denominator, and Vs, that is the volume of irrigation water stored in the root zone. Okay, this is application efficiency, and this is also cannot be 100% because there will be again runoff losses and evaporation losses and depercolation losses. Okay, so this also cannot be 100% efficiency. It is always less. And then so the application efficiency is important as for the irrigation system is considered or concerned. So for example, if you are using sprinkler irrigation system, so the efficiency could be like up to 90%. If you are using surface irrigation systems, the efficiency could be like 45 to 80% based on the type of efficiency, type of irrigation system you are using. And if it is a micro irrigation system, it can go up to 95%. Okay, so and then the third efficiency is the water storage efficiency. So again, so now we are going down to the the root zone, right? In the third efficiency. So the first efficiency we are at the field, and second efficiency we are in the field, and third efficiency we are in the root zone. You see, so in the root zone, so the Vs is the stored, right? That is stored, but VFC minus VA, so that is actually to be replaced or replenished. Okay, so VFC, the volume capacity of field, or let's say the field capacity. So field is holding some water, right? Field is holding some water, and the excess amount will be drained through gravitational effect or gravity force. So the VFC is really present inside. So what happens? The VA is the volume of water in the soil root zone prior to irrigation event. So that much water we need to replenish, right? Replenish. So whether the amount of water stored is the same what it is required, or it is less, right? So that is ES. Okay, and this is also may not be same exactly because the depopulation issue. So that's why ES cannot be again 100%. Okay, and then the irrigation efficiency, the overall irrigation efficiency. So that could be like volume of water beneficially used divided by the volume of water you supply to the field. Okay, beneficially used in the sense, So one is the evapotranspiration or leaching salts, seed bed preparation, germinate the seeds. So there, I mean, there are several things involved in it. So uh, so we are not considering the water losses. So we are only considering the beneficial use. Okay, in case of and then overall irrigation efficiency. So you can multiply the efficiencies of conveyance and application efficiency, get overall irrigation efficiency. And I think there are other efficiencies if you're considering the salts, that is effective irrigation effective irrigation efficiency. So that is you must consider the fraction of surface runoff into the picture. Okay. Um, so I think if you have more questions, let me know for as far as the irrigation efficiency are considered. Um, Otherwise, any other questions? So please explain working of centrifugal pump and cavitation also. Okay. So the working of centrifugal pump, if you remember the lifting principles, so this is one of the lifting principle is velocity to pressure head. Okay. In centrifugal pump, what happens? So there are two main parts. One is the moving part. It's called impeller, and the stationary part is called casing. Okay, so the moving part, when you switch on the pump, I mean the switch on the pump. Let's say switch on the pump. So the impeller rotates. So when the impeller rotates, the fluid which is present inside also is going to rotate, right? It's going to rotate. So that way, so the whole fluid is going to turn, right? So this is similar to the one if you have a bucket of water and you swirl it, right? So what happens if you observe? So in the middle there is a cavity. So clearly, if you observe the middle, there is a cavity is going to form, right? So and if you increase the speed, you can clearly see a clear, the cavity. Okay. So, but if you also observe the the velocities, so in the center the velocity is more compared to the velocity at the end of the bucket, right? So the same thing is going to happen inside the centrifugal pump. So when the velocity is higher at the center, so as you see in the bucket case, so there is a the low pressure is going to create, right? When your velocity increases, pressure is decreases. So because of that, what happens? So there is a suction is going to create inside the uh, at the eye of the impeller. Okay, so because of the suction, it has to pull the water from the suction line. Okay, so that is one thing. So this fluid has to transfer to the the volute casing, isn't it? Volute casing through the blades of an impeller, isn't it? So that goes radially, right? Radially. So this fluid is being thrown radially outward, and then from there the fluid will be escaped through the delivery line. Okay, so this is the I mean basic mechanism how the velocity head is being converted into pressure head. Okay, in case of centrifugal pump. So now the cavitation. So if you observe the phenomenon just explained at the center of the impeller, so when similar to the bucket, when you rotate faster and faster, what happens? The pressure or the pressure is going to very low when the pressure is less than the vapor pressure of water, right? What happens? The bubbles are going to form, right? So bubbles are going to form. So bubbles have to escape, right? Bubbles have to escape. So they will be mixed inside the fluid, and these bubbles have to transport or transfer from eye of an impeller to the the periphery of an impeller. So as I said, at the eye of an impeller, the pressure is very less, and at the extreme point, the pressure is high. So the bubbles, when they move from low pressure zone to high pressure zone, so the bubbles are going to burst, right? Because the pressure is high. So whatever the bubble comes over there needs it has to burst there. So because of this bursting action at the end of the impeller, so you would hear noisy. You will hear a noise, right? So not only that, it can damage the surface of the impeller. Suppose if the water is not in good condition or good quality, so it can react with the material of the impeller and can corrode and erode. So that's going to happen. So technically it's going to damage the impeller. Okay, so I hope you understand the cavitation part. So, and the best example in the cavitation also, I think because when you the swilling action, the temperature also going to rise. So the temperature rise is going to help in generating the bubbles. Okay, so that way, so remember, so the main thing is if the cavitation only occurs when the negative pressure is less than the vapor pressure. Okay, so in that case only the cavitation is going to happen. Then who is the remember to guard you? Okay, this thank you, sir. Okay, thank you, sir. Good. Really. Okay, so that's all. If you have more questions, let me know. It's 5:40, and yeah. Yeah, we also talked about pump characteristic curve, right? Pump characteristic curves are very important when you select a pump for your desired discharge or for your need. So when you go to the market, when you're looking for a pump, so the manufacturer has the particular chart, right? So there the pump characteristic curves are reported. So you can decide, you can see the characteristics of a particular pump, whether it is really serves your purpose or not. So first what we have to do is you have to see how much discharge you need a day, and what is the power required, right? What is the head you would like to use, or a pump. So all these things are important when you select a pump. So pump characteristic curves are very useful for that. And the other things are called affinity loss. So affinity loss are very much essential when you are changing the diameter of the impeller, and also changing the speed of an impeller. So what's going to happen if you do this to the output, like the discharge and head, BHP. So all these things are known when you are calculated based on the affinity loss. Okay, and we talked about other pumps also. For example, axial flow pumps, and then propeller pumps. So then mixed flow pumps. Both axial flow and propeller pumps are same. Mixed flow pumps have both characteristics of centrifugal pump as well as the axial flow pump. And the jet pumps are like a centrifugal pump, but only thing is it has a jetting unit. So the jetting unit will have the nozzle and throat combination, like a venturi. So some part of water from the centrifugal pump will diverted back into the venturi, and that will help in sucking more water uh, compared to regular centrifugal pump. So that's why if you want to increase the head of centrifugal pump, so you would either use a jet pump, or we have some combinations like uh, uh, combining your impellers together, right? Like in series connection, or in parallel connection. So when you are combining, different pumps in series, so your head is going to increase, but your discharge is going to be same. Whereas um, when you are connecting, the pumps in parallel, your head will be same, but your discharge will increase. Okay, I mean Q1 plus Q2. So you remember that. And then we talked about special kind of pump. It's called the hydraulic ram or ram pump. This is basically used in case of electricity shortage or no electricity, the regions of hilly regions basically. So in order to lift water from foothills to the top of the mountain, so these pumps are very helpful. Right, because it doesn't require electricity, so it's working based on the hydraulic hammer. So we all know what is hydraulic hammer. I think I talked about that in the slides. So hydraulic hammer, what happens is, so when there is a flow which is taking place and all of a sudden you obstruct the flow, so that there is a backflow is going to take place. So we are using that backflow energy for as a pressure energy. Okay, so that during the backflow, what happens, that's going to push the valve at the air chamber, and it escapes through air chamber. And then since the air is present in the air chamber, so that compresses the fluid back and closes the valve. And then the only way the fluid present in the chamber to escape is through discharge line. Okay, so that way that works. But so this is continuous as long as you have water in the source, right? As long as you have water in the source and it is continuous, like 24/7, you can pump water. But only the problem is, only you could discharge, or you can lift 1/10 to 1/20th of what you from the source, right? So this only drawback, but otherwise without electricity, you can design this hydraulic ram. Okay. Hmm. Hmm. Okay, so then after that, I think we also talked about some drainage. I think this right now it's drainage lectures are going on. So the drainage is basically to remove excess water from the surface as well as the root zone. Since our interest is to clear water or excess water from the root zone and to create the favorable environment to the crop. So we'd be interested in removing excess water from the drainage from the root zone using either subsurface drains, right, or trail drains. So I think that the design of trail drains we talked in a steady state condition, we talked in this. Um, so and also unsteady state. And at last, I think we talked about a model and drain, how we can use that end drain model to determine the spacing between the laterals. Okay, and also the depth to drain. So it's pretty interesting. If you have some time, so download this freely available that software. So play with it. I think it's a time. If you don't have questions, so we can see you. I will see you in the next live session.